Picture a moment so brief, it's almost impossible to fathom, a trillionth of a second. In that sliver of time, smaller than a blink, smaller than a thought, the entire universe was born. Not the stars, not the galaxies, not even light as we know it, but the very fabric of reality itself. This is the Planck Epoch, the first heartbeat of existence, where temperatures soared to unimaginable heights, where energy and matter were one and the same, and where the laws of physics, as we understand them, hadn't even taken shape yet. It's a realm so extreme, so alien, that even our most advanced equations struggle to describe it. Yet, this is where everything began. Think about the world around you, the gravity that keeps your feet on the ground, the light that fills your eyes, the atoms that make up your body. All of it traces back to this single, fleeting moment. The Planck Epoch was a cosmic forge where the universe's most fundamental rules were hammered into existence. Here, in a sea of pure energy, the seeds of space and time were planted. Forces we now take for granted like gravity and electromagnetism were still tangled together, indistinguishable. It was a time of infinite density, infinite heat, and infinite possibility. And in that chaos, the blueprint for everything we know was written. But how do we even begin to understand something so far beyond human experience? That's the magic of modern science. Through towering particle colliders, through the brilliance of Einstein's theories, through the relentless curiosity of physicists daring to peer into the void, we've uncovered clues about this primordial instant. And what we've found is nothing short of breathtaking. The Planck Epoch wasn't just the beginning. It was a laboratory of unimaginable scale where the universe experimented with its own laws. Today, we're going to journey back to that first trillionth of a second to explore how the cosmos went from absolute nothingness to the first whisper of structure. Buckle up, this is where physics meets wonder. To grasp the Planck Epoch, we need to stretch our minds to the very limits of scale. This wasn't just a fleeting moment, it was the universe's first coherent instant, lasting just 10 to the power of negative 43 seconds. That's a decimal point followed by 42 zeros and then a 1. If you tried to slice a single second into that many pieces, you'd run out of ways to even conceptualize such tininess. But within that incomprehensibly brief window, everything, every force, every law, every potential ingredient of reality existed in a state of perfect unity. This era gets its name from the Planck scale, a set of measurements so extreme they redefine our understanding of space and time. At these scales, even the fabric of the cosmos behaves differently. Imagine gravity and quantum mechanics, which today seem like entirely separate rulebooks, fused together into a single, seamless force. The energy was so intense that particles as we know them couldn't exist yet. Instead, the universe was a swirling ocean of raw potential, where matter and energy weren't distinct concepts but different expressions of the same underlying mystery. Why is this moment so pivotal? Because the Planck Epoch represents the edge of what physics can explain. Beyond it, our equations break down. Einstein's theory of relativity, which governs the vast cosmos, clashes with quantum mechanics, which rules the subatomic world. Under normal circumstances, these frameworks work beautifully, but when squeezed into the Planck scale's unimaginable heat and density, they collapse into contradiction. That's why scientists pursuing a theory of everything are obsessed with this era. Decoding it could reveal the missing link between the universe's largest and smallest mysteries. Yet, even without a complete theory, we can still paint a picture of this primordial chaos. Temperatures exceeded 10 to the power of 32 degrees, so hot that numbers lose meaning. Space itself hadn't yet stabilized into the smooth continuum we know. It likely foamed and rippled with quantum fluctuations, constantly creating and destroying microscopic pockets of reality. And time, it might not have flowed in any recognizable way. In this seething, lawless infancy, the universe wasn't just young. it was rewriting the rules of existence with every passing Planck second. The universe wasn't born into empty stillness. It erupted into existence as a seething, turbulent ocean of raw potential. Spacetime itself didn't yet exist in the smooth, predictable form we know today. Instead, it was a churning quantum foam, a froth of unimaginably tiny bubbles where the very fabric of reality flickered in and out of existence. Picture a pot of water at a furious boil, but instead of steam, you're seeing space and time themselves bubbling, stretching, and collapsing in a frenzy of creation and annihilation. This was the Planck Epoch's most startling feature. Spacetime wasn't a stage, it was part of the storm. In these early moments, gravity hadn't yet settled into the gentle force that guides planets and galaxies. It was entangled with the other fundamental forces, twisting and warping the newborn universe at scales so small they defy intuition. At distances of a Planck length, about a trillionth of the width of a proton, space and time lost all semblance of order. Fluctuations in energy were so violent that microscopic black holes might have formed and evaporated in an instant, popping like bubbles in the quantum foam. The universe wasn't just expanding, it was reinventing the rules of existence with every passing moment. What does this mean for the cosmos we see today? Those fleeting fluctuations in the quantum foam weren't just random noise, they were the seeds of structure. Tiny variations in density, imprinted during this chaotic dance, eventually grew into the vast cosmic web of galaxies and voids. Even spacetime's turbulent nature left its mark. Some theories suggest that the ripples we now detect in the cosmic microwave background, the faint afterglow of the Big Bang, might carry echoes of that primordial froth. It's as if the universe's first frantic breaths were frozen into the fabric of reality, waiting billions of years for us to decode them. Yet for all its chaos, the Planck Epoch also hints at an astonishing underlying order. The fact that spacetime could emerge from such turbulence that it could stabilize into the smooth continuum we rely on, suggests a deeper harmony hidden beneath the frenzy. Physicists studying quantum gravity often describe this era as a phase transition, like steam condensing into water, where the universe's fundamental properties suddenly snapped into a new configuration. One instant, there was only boiling potential. The next, the first threads of spacetime wove themselves into existence. This is why the Planck Epoch captivates scientists and dreamers alike. It's not just a chapter in cosmic history, it's a mirror reflecting the universe's most profound mysteries. How does something as intangible as spacetime crystallize from pure energy? What laws govern that transformation? Every breakthrough in quantum gravity, every experiment probing the smallest scales brings us closer to answers. And as we peer backward toward that first trillionth of a second, we're not just uncovering the past, we're glimpsing the invisible architecture of reality itself. The temperatures during the Planck Epoch weren't just hot, they rewrote the definition of heat itself. We're talking about 10 to the power of 32 Kelvin, a number so large it dwarfs anything in human experience. To put that into perspective, the core of our sun burns at a mere 15 million Kelvin, and even the most violent supernova barely reach 1 trillion degrees. But the Planck Epoch, it was 1 trillion times hotter than that, a realm where the very concept of temperature starts to lose meaning. At these extremes, energy wasn't just a property of particles, it was the fabric of existence, saturating every infinitesimal point in space with enough raw power to bend the laws of physics beyond recognition. Take the Large Hadron Collider, our most advanced tool for recreating extreme conditions. When it smashes protons together at nearly the speed of light, it generates temperatures around 10 trillion Kelvin, enough to briefly mimic the universe a millionth of a second after the Big Bang. But that's still a factor of 10 to the power of 20 short of the Planck Epoch's fury. It's like comparing a campfire to the heart of a hypernova. Even if we built a collider the size of our galaxy, we still wouldn't come close. the energy densities of that first moment were so intense that particles couldn't even form yet. Instead, the universe was a single, unified field, a perfect symmetry where every force and particle we know today remained locked together in an inseparable embrace. This staggering heat wasn't just a side effect, it was the universe's creative engine. At 10 to the power of 32 Kelvin, quantum fluctuations weren't tiny ripples but titanic upheavals, constantly birthing and annihilating microscopic pockets of spacetime. Energy wasn't confined to particles, it was space and time, twisting them into shapes we can barely imagine. Some theories suggest that under these conditions, the very structure of reality might have undergone phase transitions, like steam condensing into water, as the universe cooled and its fundamental forces began to split apart. Yet even as we marvel at these numbers, they hint at something deeper. The Planck Epoch's unimaginable temperatures weren't just a historical curiosity, they're a roadmap to the universe's hidden architecture. Today, when physicists search for a theory of everything, they're essentially trying to reverse engineer those first moments, to find the equations that could describe a reality before particles, before forces, before even space-time as we know it. It's a reminder that the universe's most extreme conditions often hold the keys to its greatest mysteries, and while we may never recreate the Planck Epoch in a lab, its echoes linger in the cosmos, waiting for us to decode them. Today's universe operates like a finely tuned machine with four distinct forces: gravity holding planets in orbit, electromagnetism binding atoms, the strong nuclear force gluing protons together, and the weak nuclear force governing radioactive decay. But rewind to the Planck Epoch, and these forces weren't just neighbors, they were one and the same. Imagine a cosmic symphony where every instrument plays a single, unified note. That's the reality physicists describe when they talk about the unified force, a primordial state where all interactions blended seamlessly into a single, all-encompassing law. Grand unified theories, or GUT, attempt to reconstruct this lost symmetry. They suggest that at energies beyond anything we can recreate, conditions so extreme they only existed in that first trillionth of a second electromagnetism, and the nuclear forces merged into a single interaction. Picture ice melting into water. Today's distinct forces were once a fluid, indistinguishable whole. Even gravity, which now feels like the odd one out, may have been part of this unity in the Planck Epoch's unimaginable heat. But as the universe expanded and cooled, this perfect symmetry shattered like glass. Forces froze out one by one, each branching off as temperatures dropped below their critical thresholds. Why don't GUTs fully explain the Planck Epoch? Because they hit a wall when gravity enters the picture. While these theories elegantly unify the electromagnetic and nuclear forces, incorporating gravity requires something even more radical. A theory of quantum gravity, like string theory or loop quantum gravity. In the Planck Epoch's seething energy soup, gravity wasn't just another force, it was intertwined with the very fabric of spacetime itself. The equations we use to describe particles and forces today simply crumple under such conditions. It's like trying to use Newton's laws to predict the dance of subatomic particles. The scales are so different that the rules need a complete overhaul. Yet, even incomplete, these theories offer breathtaking glimpses into the universe's first moments. They suggest that the forces we now consider fundamental were once different faces of the same phenomenon. The strong nuclear forces grip on atomic nuclei, the weak forces roll in radioactive decay, even the electric spark in your nerves, all trace back to a single, elegant interaction. And somewhere beneath it all, gravity's whisper hints at a deeper unity still waiting to be uncovered. What's truly humbling is realizing how much we still don't know. The Planck Epoch's unified force exists at energies so far beyond our reach that testing these ideas directly might never be possible. But like detectives piecing together a crime scene from faint clues, physicists scrutinize the universe's oldest light, hunt for exotic particles, and push colliders to their limits. Every anomaly in particle behavior, every unexpected ripple in spacetime could be a fragment of that original symmetry, a message from the universe's first unimaginable instant. This isn't just theoretical gymnastics. Unifying forces isn't about tidying up equations, it's about uncovering the universe's deepest logic. If we could peer past the veil of the Planck Epoch, we might finally answer why our cosmos has the rules it does. Were these forces always destined to split, or was it a random roll of the quantum dice? For now, the unified force remains both a tantalizing mystery and a beacon, guiding us toward a theory of everything, one that could rewrite not just our understanding of the Big Bang but reality itself. Hidden in the chaos of the Planck Epoch's seething energy was a delicate fingerprint: quantum fluctuations so small they defy belief, yet powerful enough to shape the entire cosmic landscape. These weren't just random ripples in the primordial soup. They were the universe's first brushstrokes, invisible imperfections that would one day grow into galaxies, stars, and everything we see. Imagine shaking a snow globe with infinite force. The swirling blizzard inside isn't pure chaos. Tiny differences in how each flake moves eventually determine where the snow settles. That's what happened in those first moments. The universe's frenetic energy didn't distribute itself perfectly. Microscopic variations in density, smaller than a single atom, were baked into reality, and they carried the blueprint for everything to come. Fast forward billions of years, and we see their legacy. The cosmos isn't a uniform sea of matter. It's a vast web of galaxies clustered along invisible filaments with yawning voids in between. This structure didn't emerge by accident. It traces back directly to those quantum tremors during the Planck Epoch, stretched and amplified by cosmic inflation, the universe's explosive growth spurt. Inflation acted like a cosmic magnifying glass, taking those subatomic wrinkles and blowing them up to astronomical proportions. What began as fluctuations spanning a Planck length, a billionth of a trillionth of a proton's width, became the gravitational seeds for galaxy clusters. The denser regions pulled in more matter, while the emptier zones stretched into voids. The universe, in essence, remembered its quantum beginnings. Here's the astonishing part: we've actually seen these primordial fingerprints. The cosmic microwave background, the afterglow of the Big Bang, is riddled with temperature variations, slightly hotter here, slightly cooler there. These patches match the distribution of galaxies today. It's as if we're staring at a baby photo of the cosmos, and the freckles on its face grew up to become cities of stars. Without those early quantum fluctuations, the universe might have been a featureless void, forever dark and silent. Instead, they gave gravity something to work with, kickstarting the slow dance of structure formation that led to planets, life, and us. But how could something so small wield such cosmic influence? The answer lies in inflation's exponential stretching. Picture a balloon with a barely visible crease. Blow it up to the size of Earth, and that tiny floor becomes a canyon. Now imagine blowing it up to the size of the observable universe in a fraction of a second. That's what inflation did to quantum fluctuations. The process didn't just enlarge them, it locked their pattern into the fabric of spacetime, ensuring they grew alongside the universe itself. What's even more mind-bending is that these fluctuations might owe their existence to spacetime's fuzzy, quantum nature. At Planck scales, empty space isn't truly empty. It's a turbulent sea of virtual particles popping in and out of existence, a phenomenon called quantum foam. These fleeting disturbances could have left permanent scars in the form of density variations, like footprints in wet sand after the tide recedes. Some theories even suggest that spacetime's own granularity, the idea that it's not smooth but pixelated at the smallest scales, played a role in creating those initial seeds. This isn't just theoretical sleight of hand. Supercomputer simulations that model the universe's evolution, starting from these tiny fluctuations, produce structures eerily similar to the cosmic web we observe. The math matches the sky. And while we can't directly observe the Planck Epoch's quantum froth, its echoes ripple through the cosmos in the distribution of galaxies, the polarization of ancient light, even the way black holes merge. Every new telescope, from James Webb to next-generation gravitational wave detectors, brings us closer to decoding those whispers from the dawn of time. So the next time you look up at the night sky, remember, the constellations above you owe their existence to quantum jitters so small they'd make an atom look like a galaxy. The universe didn't just emerge smooth and uniform, it was born with texture, with potential, with flaws that became its greatest features. And in those imperfections, written in the language of probability and uncertainty, lies the origin of everything. The Planck Epoch doesn't just push the boundaries of physics, it shatters them. This is where our two most successful theories of reality, general relativity and quantum mechanics, reach their breaking points. One governs the cosmos on the grandest scales, bending spacetime itself. The other rules the subatomic realm, where particles pop in and out of existence like bubbles in a quantum foam. Individually, they're brilliant, precise, and endlessly tested. But in the Planck Epoch's extreme conditions, where spacetime is compressed to a billionth of a trillionth of a proton's width and energies reach impossible densities, they become impossible to reconcile. General relativity paints gravity as the curvature of smooth, continuous spacetime, a cosmic trampoline warped by massive objects. But in the quantum world, everything is graininess and uncertainty. There's no such thing as smooth at the Planck scale. Spacetime itself becomes a seething, probabilistic foam. Picture trying to describe the flow of a river using equations designed for individual water molecules. The math collapses. This clash isn't a minor technical hurdle, it's a fundamental rift in our understanding of reality. When relativity's elegant curves meet quantum mechanics' chaotic flickers, the result isn't harmony. It's a cacophony of infinities and paradoxes screaming for a deeper theory. That's why the Planck Epoch is more than a historical curiosity, it's a laboratory for the impossible. To peer into this era, we'd need a framework where gravity behaves quantumly, where spacetime itself can split, merge, or fluctuate. String theory offers one tantalizing path, proposing that particles aren't dots but vibrating strings, and that extra dimensions might hide gravity's quantum nature. Loop quantum gravity takes another approach, suggesting spacetime is woven from tiny, indivisible loops like a cosmic fabric stitched together at the smallest scales. Even emergent gravity theories flip the script entirely, proposing that gravity isn't fundamental but arises from deeper quantum interactions, like temperature emerging from atomic motion. Yet all these ideas share a common thread. They recognize that the Planck Epoch wasn't governed by today's fragmented laws. It was a realm of perfect unity, where the distinctions between force and field, between particle and wave, between here and now hadn't yet crystallized. Solving this puzzle isn't just academic, it's the key to unlocking reality's deepest secrets. The universe didn't start with separate rules for the big and the small. Those divisions came later. To understand the Planck Epoch is to glimpse the universe before it forgot its original language. That's what makes this frontier so thrilling and so humbling. Every observation we make, from the spin of black holes to the afterglow of the Big Bang, carries whispers of that primal unity. But until we crack quantum gravity, those whispers remain just out of earshot. The Planck Epoch stands as both a challenge and an invitation to rewrite physics not from the ground up but from the beginning out, and somewhere in that first trillionth of a second, the answers are waiting. String theory offers a radical rewrite of the Planck Epoch's chaos, one where the universe's tiniest building blocks aren't dots but wriggling, vibrating filaments of energy. Imagine plucking a guitar string and hearing not just one note, but every possible note at once, each vibration corresponding to a different particle. That's the core idea. Electrons, quarks, even the carriers of forces like photons aren't zero-dimensional points but tiny loops or strands, each humming at a unique frequency. In the Planck Epoch's inferno, these strings wouldn't just interact, they'd be spacetime itself, weaving the fabric of reality from their endless dance. This isn't just poetic imagery. String theory's mathematical backbone suggests that at energies beyond our current collider's reach, conditions that only existed in that first trillionth of a second, particles lose their individual identities. The distinctions between matter and force carriers blur, as every string's vibration pattern determines whether it manifests as an electron, a graviton, or something entirely unknown. And here's where it gets wild. These strings don't vibrate in just 3 dimensions of space and 1 of time. They require extra dimensions, possibly 10 or 11 in total, curled up so tightly that even the Planck length seems vast by comparison. Why higher dimensions? Because strings need room to vibrate in more complex ways, like how a guitar's sound changes if you add extra strings. In the Planck Epoch, these hidden dimensions might have been stretched wide open, creating a universe far stranger than today's. Gravity, notoriously aloof in quantum physics, could have been just another vibration mode in this multidimensional symphony, the violent quantum foam we've discussed. It might have been a turbulent sea of intersecting strings, constantly splitting and merging in a geometric ballet. But string theory's real magic lies in how it smooths over the Planck Epoch's paradoxes. When general relativity predicts infinite densities and quantum mechanics spews probabilities, strings step in with an elegant fix. Their finite size prevents the mathematical singularities that plague point particles. A string can't collapse to zero volume. It always has length, so the universe's birth becomes less a Big Bang singularity and more a big stretch, where strings dilute the chaos by spreading energy across their extended forms. Critically, this framework doesn't just tweak the Planck Epoch's physics, it reimagines causality itself. With strings intertwining in extra dimensions, events we'd consider impossibly distant in 3D space could have been neighbors along a hidden axis. Particles might have communicated faster than light by taking shortcuts through these folds, explaining how the young universe achieved such startling uniformity. Even the concept of before and after gets fuzzy, as strings vibrating through time-like dimensions could have created feedback loops where cause and effect blur. Yet for all its elegance, string theory faces fierce challenges. We've yet to observe strings or extra dimensions directly. They're simply too small and too energy-intensive to probe with current technology. Some critics argue it's more mathematical art than testable science, but defenders counter that the Planck Epoch itself is beyond direct observation, and string theory remains the most cohesive bridge between quantum mechanics and gravity we've devised. Its equations naturally describe the unified force we suspect governed that era, and they hint at even deeper symmetries hidden beneath spacetime's surface. Perhaps most tantalizing is how string theory reshapes our view of cosmic origins. If correct, the Planck Epoch wasn't just a hot, dense state, it was a higher dimensional arena where strings orchestrated reality's very rules. As the universe cooled, those extra dimensions collapsed, leaving only the familiar 4 we experience today. The vibrations that once birthed particles and forces froze into the diverse tapestry we now observe. In this light, the Planck Epoch wasn't an end of understanding but a gateway, a glimpse into a richer, more interconnected cosmos than we ever imagined. While string theory weaves spacetime from vibrating strings, loop quantum gravity takes a dramatically different path. It stitches the universe together with tiny, indivisible knots. Picture space not as a smooth, continuous expanse, but as a fabric made of intersecting threads, each one a billionth of a trillionth of a millimeter long. In this framework, spacetime isn't just curved, it's granular, built from woven loops that define its very structure. When applied to the Planck Epoch's maelstrom, This vision transforms the cosmic beginning from a singularity into a dynamic quantum network where spacetime itself emerges from the dance of these elemental threads. At the heart of loop quantum gravity is a radical reimagining of Einstein's spacetime. Instead of treating gravity as curvature on a smooth backdrop, it quantizes space itself, breaking it into discrete atoms of volume. Think of it like pixels on a screen. Just as digital images are built from tiny dots, spacetime in this theory is composed of finite loops, each carrying its own quantum of area or volume. During the Planck Epoch, these loops wouldn't have formed a calm grid. They'd have been a frenzied web, constantly reconnecting and fluctuating, with energy so dense that space and time lost all classical meaning. Gravity here isn't a force acting on spacetime. It is spacetime evolving through the quantum interactions of these loops. How does this solve the paradoxes of the Planck Epoch? In general relativity, the Big Bang starts as a singularity, a point of infinite density where physics breaks down, but loop quantum gravity erases that infinity. Because space can't be squeezed smaller than the loops themselves, there's a hard limit to compression. Instead of a singularity, the theory predicts a quantum bounce, a moment where collapsing space rebounds like a compressed spring hitting its limit. In this view, the Planck Epoch wasn't the absolute beginning, but a transition from a previous universe's collapse, with spacetime surviving the journey thanks to its woven, resilient structure. The theory also reshapes our understanding of the quantum foam. Rather than a froth of virtual particles, it describes spacetime as a spin network, a graph of interconnected loops where each intersection represents a quantum of volume and each link carries a quantum of area. Under the extreme energies of the Planck Epoch, this network wouldn't just fluctuate, it would pulse with loops merging and splitting in a chaotic ballet. Time in this context might not flow smoothly but advance in discrete jumps, like frames in a cosmic film reel. It's a universe where even causality becomes granular, with events tied to the evolving connections between loops. Where string theory leans on extra dimensions, loop quantum gravity keeps things local. Its loops live in the three spatial dimensions we know, plus time. This simplicity is both its strength and its challenge. Without higher dimensions to hide complexities, the theory must confront quantum gravity's toughest problems head-on. Yet it also offers startlingly concrete predictions. For instance, it suggests that spacetime's granularity could leave imprints on high-energy photons traveling across the universe, subtly altering their speeds. Telescopes hunting gamma-ray bursts are now searching for these telltale signs, hoping to catch whispers of the Planck Epoch's loops in today's cosmos. But perhaps the most profound implication is how loop quantum gravity redefines nothingness. In this framework, even the vacuum of space isn't empty, it's a seething network of potential loops, a spacetime in waiting. The Planck Epoch, then, wasn't a static starting gun but an explosive reorganization of this quantum tapestry, where loops aligned into the stable fabric we now inhabit. It's a reminder that the universe's birth might not have been a singular event, but a phase change, an emergence of order from chaos like crystals forming in a cooling melt. String theory and loop quantum gravity may seem like rivals, but they share a deeper truth. Both point toward a reality where spacetime isn't fundamental but relational, built from something more primordial. Whether strings or loops, the message is the same. The Planck Epoch's extremes demand a physics beyond smooth continua, where the universe's bones are quantum, tangled, and alive with possibility. The answers may lie not in choosing one theory over the other, but in recognizing that both are glimpses of a truth still just beyond our grasp. Black holes might seem like cosmic monsters, devouring everything in their path, but they hold a secret, one that links them directly to the universe's fiery birth. At their cores, black holes warp spacetime so severely that the laws of physics as we know them break down, echoing the extreme conditions of the Planck Epoch. And here's the twist. These gravitational behemoths obey the same thermodynamic rules as steam engines and refrigerators. This bizarre connection between black holes and heat, first proposed by Jacob Bekenstein and later expanded by Stephen Hawking, reveals that entropy, the measure of disorder in a system, isn't just a property of matter but of space-time itself. In other words, the universe's earliest moments might have been governed by a kind of cosmic thermodynamics, where energy, gravity, and information were locked in a dance we're only beginning to understand. Consider Hawking radiation, the slow leakage of energy from black holes. According to quantum theory, pairs of virtual particles constantly flicker in and out of existence near a black hole's event horizon. Occasionally, one particle falls in while the other escapes, carrying energy away. Over eons, this process causes black holes to evaporate, but here's the catch: the radiation isn't random. It carries a precise temperature directly tied to the black hole's surface gravity, a clear signature of thermodynamics at work. If black holes, the most extreme gravitational objects we know, obey these rules, then the Planck Epoch's unimaginable energy densities might have behaved similarly. The young universe could have been a cauldron where gravity and thermodynamics were indistinguishable, a place where entropy wasn't just a consequence of physics but its driving force. This link becomes even more intriguing when we examine entropy's role in the early cosmos. In today's universe, entropy increases over time, the famous arrow of time pointing toward disorder. But during the Planck Epoch, entropy might have been fundamentally different. Some theories suggest that spacetime itself had a maximum entropy limit, a sort of cosmic saturation point where gravity and quantum effects balanced perfectly. Black holes, as it turns out, are nature's entropy maximizers. Their event horizons contain more entropy than any other object of the same size. If the Planck Epoch spacetime behaved like a black hole's interior, packed with energy at the smallest scales, then its entropy could have dictated the universe's initial structure. Those tiny quantum fluctuations we see imprinted on the cosmic microwave background, they might be entropy's fingerprints, frozen into the fabric of reality as spacetime cooled. What does this mean for the Big Bang? If black hole thermodynamics applies, the universe's birth wasn't just a violent expansion but a thermodynamic phase transition, like water turning to steam in reverse. The Planck Epoch's heat wasn't just temperature, it was the energy of spacetime itself churning with quantum activity. And just as Hawking radiation bridges quantum mechanics and gravity, a deeper thermodynamic principle might have bridged the Planck Epoch's chaos with the orderly cosmos that followed. This perspective reshapes how we view cosmic origins, not as a singularity, but as a moment of supreme thermodynamic imbalance where the universe's first engine converted pure energy into the seeds of structure we see today. The implications are staggering. If black holes and the Planck Epoch share thermodynamic rules, then studying one illuminates the other. Observations of evaporating black holes, should we ever detect Hawking radiation directly, could reveal how information escapes a gravitational prison, a process that might mirror how the early universe encoded its initial conditions. Similarly, simulations of quantum gravity that replicate black hole behavior could offer clues about spacetime's behavior in those first moments. The universe's past and its most enigmatic objects are whispering the same story. Thermodynamics isn't just a law of the everyday world. It's the hidden language of creation itself, written in the heat of black holes and the afterglow of the Big Bang. The concept of time seems so fundamental, we measure it, rely on it, perceive its passage. But when we peer back to the Planck Epoch, even this bedrock assumption begins to unravel. Did time exist before that first trillionth of a second, or was it born alongside space, energy, and matter in the Big Bang's crucible? This isn't just a physics puzzle, it's a question that blurs the line between science and philosophy, forcing us to reconsider what before even means when the clock itself might not have been ticking. One radical answer comes from Stephen Hawking and James Hartle's no boundary proposal, which reimagines the universe's origin as a smooth, self-contained bubble with no sharp edges, no beginning in the traditional sense. Picture Earth's North Pole. There's no point north of it, yet the surface extends seamlessly around. Similarly, the no-boundary model suggests time didn't abruptly start at the Big Bang, but gradually emerged from a timeless quantum state. In this view, asking what came before is like asking what's south of the South Pole, a question that loses meaning when the framework itself shifts. The Planck Epoch, then, wasn't the first moment in time, but the moment time crystallized from something deeper and stranger, yet not all cosmologists agree. Cyclic models propose a universe that breathes, expanding and contracting in endless cycles, each Big Bang preceded by a big crunch. Here, time stretches indefinitely backward, with the Planck Epoch marking not a true beginning but a rebound, like a ball bouncing at the bottom of a cosmic well. Some versions even suggest information survives these cycles, meaning the universe might carry scars from its past incarnations. Imagine a book where each chapter ends in flames, only for the next to begin with its ashes rearranged into new words. The Planck Epoch's extreme conditions would be the furnace where one universe's collapse forges another's birth, with time as the unbroken thread weaving through each iteration. But there's a catch. Both approaches grapple with the same enigma. Our laws of physics dissolve at the Planck scale. General relativity treats time as a smooth continuum, while quantum mechanics chops it into discrete, flickering moments. Reconciling these views requires something beyond both: a theory where time isn't primary but emergent, like temperature arising from atomic motion. Loop quantum gravity, for instance, suggests time might be a side effect of changing relationships between quantum loops, not an independent flow. If true, the Planck Epoch wasn't just before time, it was outside it, a realm where cause and effect tangled into knots. Even language struggles here. Words like before and after assume time's existence, creating a paradox when we try to describe its absence. Some theorists sidestep this by framing the Planck Epoch as a quantum phase transition, where time condensed like dew on a cold surface. Others argue time might have multiple arrows in those early moments, flowing in ways we can't yet model. The most provocative idea, that time's direction, its relentless march forward, isn't fundamental but a consequence of entropy's rise, a thermodynamic accident frozen into the universe's bones during the Planck Epoch's cooling. What's clear is that our everyday intuition about time fails spectacularly at these extremes. Whether it's Hawking's timeless bubble, a cyclic universe's eternal rhythm, or a quantum leap from nothingness, the Planck Epoch remains the ultimate mirror, reflecting our deepest uncertainties about reality's foundations. Until we crack quantum gravity's code, these theories are like maps of a territory we've never seen, each revealing glimpses, but none yet the full picture. And that, perhaps, is the most exhilarating part. The Planck Epoch doesn't just hide the universe's origin story. It challenges us to rewrite the very meaning of beginning. Deep within the Planck Epoch's chaos, where spacetime itself was still taking shape, there may have existed the most fundamental building blocks conceivable: Planck particles. These hypothetical entities, each with a mass equal to the Planck mass and a size matching the Planck length, represent the ultimate limit of how small and dense matter can become without collapsing into a black hole. Picture a speck so tiny that if you enlarged it to the size of a grain of sand, an atom would still dwarf it by the same scale. Yet despite its minuscule size, a single Planck particle would weigh more than a grain of pollen, a staggering concentration of mass energy crammed into a volume smaller than anything we've ever observed. Why does this matter? Because Planck particles aren't just curiosities, they're potential keys to unlocking quantum gravity. In the Planck Epoch's extreme conditions, where even protons and electrons couldn't yet form, these particles might have been the only stable structures, existing in a fleeting equilibrium between gravitational collapse and quantum repulsion. Their mass is precisely tuned to a cosmic sweet spot. Any heavier, and they'd instantly implode into black holes. Any lighter, and they'd dissolve into the quantum foam. This delicate balance makes them ideal candidates for bridging the chasm between quantum mechanics and general relativity, offering a glimpse into how matter behaves when both theories exert equal influence. But here's the catch: Planck particles are forever beyond our direct observation. Their minuscule size means detecting them would require a particle accelerator the size of a galaxy, a machine with energies quintillions of times beyond our current technology. Even if we somehow created one, it would evaporate in a flash of Hawking radiation long before we could study it. Yet their theoretical existence reshapes how we think about the early universe. If Planck particles did flicker into being during the Planck Epoch, they might have acted as cosmic anchors, stabilizing spacetime's turbulence long enough for larger structures to emerge. Some theories even suggest they could have been the seeds for primordial black holes, those mysterious relics from the universe's first moments that might still lurk unseen in today's cosmos. What makes Planck particles so tantalizing is their dual nature. They're not just particles but also gravitational hotspots, blurring the line between matter and space-time curvature. In a sense, they embody the dream of unification that drives quantum gravity research, a single entity where mass, energy, and geometry merge into one. Whether they truly existed or remain mathematical phantoms, their study forces us to confront the wildest frontiers of physics, where the ordinary rules dissolve and the universe reveals its deepest secrets. The Planck mass sits at the crossroads of the universe's most extreme scales, a seemingly modest 22 micrograms, yet packed with cosmic significance. To grasp why this tiny mass matters, imagine compressing the energy of a small nuclear explosion into a speck smaller than a single dust particle. That's the Planck mass, a threshold where gravity's pull becomes so strong it rivals the other fundamental forces, and quantum effects start warping spacetime itself. In the Planck epoch, this wasn't just another value on a scale. It was the ultimate energy ceiling, a barrier nature couldn't exceed without rewriting its own rules. Compare this to the Higgs boson, the heaviest elementary particle we've detected, with a mass about 100 billion times lighter than the Planck mass. The Higgs is a featherweight in this arena. Its discovery required the colossal Large Hadron Collider, but to probe particles approaching Planck-scale energies, we'd need a collider the size of a galaxy. The gap between these masses isn't just quantitative, it's a chasm separating the known from the speculative. While the Higgs helps explain how particles gain mass in today's universe, the Planck mass hints at a deeper layer of reality, where gravity and quantum mechanics merge inseparably. Why does this limit exist? At energies matching the Planck mass, particles become so dense they risk collapsing into microscopic black holes. Gravity, usually negligible in particle physics, suddenly dominates, curving spacetime into a closed loop around the particle. It's as if the universe imposes a speed bump here, preventing matter from reaching densities that would blur the line between particle and singularity. During the Planck epoch, this balance was critical. Particles couldn't grow arbitrarily massive without destabilizing the fledgling fabric of spacetime. The Planck mass also defines the frontier of quantum gravity. Below it, particles behave predictably. Above it, their gravitational fields overwhelm quantum uncertainty, creating paradoxes. Picture trying to balance a marble on the tip of a needle. The Planck mass is the point where the marble's weight snaps the needle. This duality makes it a Rosetta Stone for theorists, a mass where the equations of general relativity and quantum mechanics both fail spectacularly, forcing us toward a deeper theory. Yet for all its abstraction, the Planck mass might have left fingerprints on the cosmos. Some models suggest primordial black holes, those mysterious relics from the universe's first moments, could have formed with masses near this scale. These tiny gravitational traps, if they exist, would be screaming clues about the Planck epoch's physics. Others speculate that the Planck mass set the energy ceiling for cosmic inflation, determining how fiercely the universe expanded in its infancy. What's astonishing is how this seemingly obscure value connects to everyday experience. The Planck mass is roughly the weight of a grain of pollen, a reminder that the universe's most profound limits sometimes hide in plain sight. It's a cosmic speed limit, a gravitational tipping point, and perhaps a key to unlocking physics beyond Einstein. And while we may never directly probe particles at this mass, its shadow looms over every attempt to unite gravity and quantum mechanics, whispering that the answers we seek are written in the language of extremes. The holographic principle turns our understanding of reality inside out literally. It suggests that everything we perceive in 3 dimensions, from swirling galaxies to the atoms in your hand, might actually be encoded on a distant 2-dimensional surface like a cosmic projector screen. This isn't science fiction. It's a serious theory born from the study of black holes, where physicists discovered that all the information swallowed by these gravitational monsters could be perfectly preserved on their event horizons. Apply this idea to the Planck Epoch, and suddenly, the universe's fiery birth takes on a startling new dimension. Picture the early universe not as a seething ball of energy in 3D space, but as a flickering hologram, a shimmering sheet of fundamental information where every particle, every force, even spacetime itself, is just a projection from a deeper, simpler reality. In this view, the Planck Epoch's chaos wasn't confined to 3 dimensions. It was the unfolding of a cosmic code written in 2. The holographic principle implies that the universe's most extreme conditions might have been far more organized than they appeared, with complexity emerging from a hidden, lower-dimensional blueprint. Why does this matter for understanding the Planck Epoch? Because it offers a radical solution to one of physics' biggest headaches: how to reconcile gravity with quantum mechanics. In a holographic universe, gravity in 3D space could emerge from quantum interactions on a 2D surface, much like the pixels on your phone screen create the illusion of depth. During the Planck Epoch, when gravity and quantum effects were inseparable, this duality might have kept the universe stable. Instead of infinite densities and singularities, the Big Bang could have been a transformation, a holographic phase change where information rearranged itself from 2 dimensions into 3. The implications are dizzying. If the holographic principle holds, then the quantum fluctuations that seeded galaxies weren't just random noise. They were pixels on a primordial canvas, their patterns dictated by a deeper, theoretical surface we can't yet observe. Even spacetime's foam-like structure might be a shadow of this underlying code, a glitch in the projection from 2D to 3D. Some theorists go further, suggesting that the Planck length itself, the smallest meaningful distance, could represent the pixel size of this cosmic hologram, setting a fundamental limit on how finely reality can be sliced. Critics argue the holographic principle remains untested, a beautiful idea without experimental proof. But supporters point to tantalizing clues. Certain mathematical models of black holes, when viewed holographically, suddenly resolve paradoxes about information loss. Simulations of quark-gluon plasma, a state of matter resembling the Planck Epoch soup, behave unexpectedly like fluid dynamics in fewer dimensions. These hints suggest the universe might literally be performing a dimensional magic trick with the Planck Epoch as its opening act. What's truly humbling is realizing how much we still don't know. The holographic principle doesn't just challenge our models of the early universe, it redefines what reality means. If correct, then our 3D world is an illusion, a shadow play cast by something far stranger. The Planck Epoch's violence might not have been the birth of space and time, but the moment a flat, encoded surface conspired to trick us into seeing depth. And somewhere, hidden in the math, lies the universe's original language, not written in particles or forces, but in pure, minimalist information. From the Planck Epoch's quantum turbulence, the universe didn't just expand, it exploded, stretching from subatomic scales to cosmic proportions in a fraction of a second. This wasn't ordinary growth, it was cosmic inflation, a runaway repulsion woven into the fabric of spacetime itself, and its trigger might lie buried in those first moments of unified forces and seething energy. One leading theory points to a hypothetical energy field called the inflaton, a scalar field that permeated the Planck Epoch's chaos. Picture a ball resting atop a steep hill. The inflaton represented an unstable high-energy state, like the ball poised to roll. As the universe cooled past a critical threshold, this field rolled downhill, releasing energy that powered inflation's breakneck expansion. The inflaton wasn't a particle or force, but a kind of cosmic clockwork, its decay converting raw potential into spacetime's explosive stretching. Remarkably, quantum jitters in this field could explain the density variations we see imprinted on today's cosmos, tiny wrinkles magnified into galaxy clusters. But the inflaton isn't the only contender. Some models suggest inflation sprang from a phase transition in the primordial unified force, like steam condensing into water, but with spacetime as the medium. During the Planck Epoch, gravity, electromagnetism, and nuclear forces were indistinguishable. As temperatures dropped, this symmetry shattered, releasing latent energy that fractured spacetime's structure. Think of it as a cosmic dam breaking. The sudden separation of forces unleashed a flood of energy, catapulting the universe into hyperdrive. A wilder idea ties inflation directly to quantum gravity. If spacetime was granular in the Planck Epoch, composed of loops or strings, its rapid expansion might have been a thermodynamic inevitability, like gas filling a vacuum. Just as steam expands to balance pressure, the universe's quantum geometry could have sought equilibrium, smoothing wrinkles and diluting defects in the process. This perspective frames inflation not as an external trigger, but as spacetime's natural response to its own extreme birth pangs. Critically, these theories aren't mutually exclusive. The inflaton could have emerged from a phase transition, or quantum gravity's rules might have dictated the field's behavior. What unites them is the Planck Epoch's role as a crucible. Whether through fields, forces, or fundamental geometry, the seeds of inflation were sown when the universe was too young for stars, atoms, or even light. The echoes of that explosive growth still resonate today, etched into the distribution of galaxies and the whisper of cosmic microwaves, a relic of the moment the universe rewrote its own rules. What if our universe isn't alone? The Planck Epoch's unimaginable energies might have done more than birth our cosmos. They could have sparked an entire multiverse. Picture a boiling pot of water with bubbles forming and popping at random. Now imagine each bubble isn't steam, but an entire universe budding off from the chaotic quantum foam of those first moments. This isn't science fiction, it's a leading theory called eternal inflation, where the same forces that stretched our universe into existence never truly stopped, endlessly birthing new cosmic realms beyond our horizon. At the heart of this idea lies inflation's peculiar nature. When the inflaton field, that hypothetical energy driver of cosmic expansion, decayed in our corner of reality, it released energy that smoothed and stretched spacetime. But what if some regions decayed faster than others? Think of it like a forest fire where patches of wet ground resist burning. In cosmic terms, pockets where inflation ended became universes like ours, while others kept expanding exponentially, spawning new inflating regions that birthed their own universes in turn. The Planck Epoch's quantum fluctuations would have seeded these variations, meaning the multiverse's roots trace back to spacetime's very first tremors. Bubble universes offer one compelling vision of this process. Each bubble forms with its own unique physics, like soap suds floating in a tub with different colors and sizes. Some might have stronger gravity or extra dimensions. Others could lack electromagnetism altogether, rendering stars and life impossible. Crucially, These bubbles don't collide or interact, they're separated by eternally inflating space, forever out of reach. This explains why we've never detected another universe. The space between them stretches faster than light can cross it. Yet their existence could answer why our cosmos seems oddly fine-tuned for life. If countless universes with random physical constants exist, it's no surprise we find ourselves in one where those constants allow galaxies, planets, and us. But bubbles aren't the only multiverse scenario birthed in the Planck Epoch. String theory's landscape of possible vacuum states, each representing a distinct universe, suggests another path. When the unified forces of the Planck era fractured, they might have froze into different configurations across space, like water crystallizing into ice with varied grain patterns. Each patch with a unique freezing pattern became a universe with its own laws. Meanwhile, quantum gravity's fuzzy nature might have allowed parallel timelines to branch off during that critical first instant, creating a many-worlds multiverse at a cosmic scale. The Planck Epoch's extreme conditions make it a perfect incubator for these theories. With spacetime's fabric still malleable and energies high enough to warp causality itself, the rules we take for granted might have been in flux. A quantum fluctuation that stabilized one way here could have stabilized differently elsewhere, spawning realities where time flows backward or entropy decreases. Even the holographic principle hints at a deeper layer where multiverses are encoded on a shared boundary, like multiple movies stored on the same hard drive. Skeptics argue these ideas are untestable philosophy dressed as physics. Yet subtle clues might lurk in the cosmic microwave background's patterns or gravitational wave signatures, remnants of our bubble universe brushing against others. Others propose that the Planck Epoch's physics left imprints on dark matter or neutrino behavior, hidden signals of sibling universes. While definitive proof remains elusive, the multiverse framework reshapes how we see our universe's birth, not as a singular event, but as one page in an infinite cosmic library, with the Planck Epoch as its explosive prologue. The Planck Epoch's unfathomable energies didn't just shape the visible universe, they might have forged its darkest secrets. Dark matter and dark energy, those enigmatic forces driving cosmic expansion and galactic structure, could trace their origins to the universe's first trillionth of a second. Picture the Planck Epoch not just as a fireball of particles and radiation, but as a cauldron brewing exotic ingredients we've yet to detect. Among the swirling quantum foam and seething unified forces, something strange may have crystallized, something invisible, pervasive, and far stranger than anything in our current physics playbook. Take dark matter first. Most theories assume it's a relic particle left over from the early universe, but what if it's older than atoms, older than light itself? Some models suggest dark matter could be primordial, emerging directly from the Planck Epoch's chaos as spacetime itself stabilized. One candidate, Planck-scale black holes, microscopic gravitational knots that formed when quantum fluctuations collapsed under their own gravity. These tiny monsters would have evaporated instantly, but not without consequence. Their quantum debris, hypothetical particles like WIMP, weakly interacting massive particles, or even more exotic entities, might have flooded the young universe, persisting as dark matter's invisible scaffold. Alternatively, dark matter could be a frozen quantum field, a remnant vibration from when gravity and other forces were still entwined, like a cosmic fossil humming beneath reality's surface. Dark energy's roots might dive even deeper. If inflation was driven by a scalar field like the inflaton, could a similar field still linger, now gently pushing galaxies apart? The Planck Epoch's unified forces might have birthed not just the inflaton, but other hidden fields that only revealed themselves billions of years later. Imagine a dormant energy woven into spacetime during its fiery birth that awakens when the universe grows large enough, like a coiled spring finally releasing its tension. Quantum gravity theories add another twist. Dark energy could be spacetime's memory of its own granularity, a low-energy echo of the Planck Epoch's fractal geometry trying to reassert itself. The most radical ideas blur the line between dark matter and dark energy entirely. In certain string theory models, both phenomena stem from higher dimensional vibrations left over when the universe's extra dimensions collapsed. Picture a cosmic orchestra where some musicians are trapped behind a curtain. Their music shapes the room, but you never see them play. Similarly, dark matter and energy might be shadows of processes unfolding in dimensions beyond our perception, their influence leaking into our universe during the Planck Epoch's dimensional reshuffling. Critically, these aren't just speculative daydreams. Observations of galaxy rotation curves and the cosmic microwave background already hint that dark matter's behavior aligns with predictions for ultra-heavy particles from the early universe. Dark energy's acceleration, meanwhile, matches calculations of vacuum energy, suggesting it might indeed be a field frozen at near Planck-scale energies. Upcoming experiments, from ultra-sensitive dark matter detectors to next-gen telescopes mapping the universe's expansion, could finally spot these ghosts of the Planck Epoch in action. What's striking is how these mysteries loop back to the universe's first moments. Dark matter's gravitational grip and dark energy's push might not be separate phenomena at all, but two faces of the same primordial coin, a reminder that the Planck Epoch didn't just create the universe we see. It built the shadows we're still straining to understand. The very notion of information might seem abstract bits of data, the spin of particles, the state of a quantum field, but in physics, information is sacred. It cannot be created or destroyed, only transformed. This principle holds true in our everyday world, from burning logs turning to ash to computers processing code. Yet when we rewind to the Planck Epoch, where spacetime itself was still flickering into existence, the rules get murky. Here, in that first trillionth of a second, the universe faced its own version of the black hole information paradox. If the primordial fireball was a cosmic blender, churning energy into oblivion and back, how could any trace of its initial conditions survive? Black holes famously threaten information's immortality. When matter falls into one, it seemingly vanishes, leaving only mass, charge, and spin, a violation of quantum mechanics' insistence that information must persist. The Planck Epoch's extreme conditions mirror this dilemma. Imagine the universe's birth as a quantum fluctuation so violent it risked erasing its own blueprint. Quantum fields collided, spacetime bubbled, and particles annihilated faster than they could form. In such chaos, how could the universe remember its starting point well enough to evolve into the structured cosmos we see today? The answer might lie in one of physics' most bewildering phenomena, quantum entanglement. Entanglement links particles across distances so that measuring one instantly affects its partner, no matter how far apart. During the Planck Epoch, this spooky connection could have acted as cosmic glue, weaving information into the fabric of reality itself. Picture two particles born together in the primordial foam. Even as inflation stretched them light years apart, their quantum states remained correlated, preserving a hidden thread of the universe's initial conditions. This intricate web of entanglement might explain how the cosmos retained coherence despite its violent beginnings, like a symphony whose notes stay in harmony even when scattered across space. Yet entanglement alone doesn't resolve the paradox. Enter the firewall hypothesis, a radical idea born from black hole physics. If information can't be destroyed, but also can't escape a black hole's grip, some theorists argue the event horizon must be a searing wall of energy, a firewall that scrambles information into unrecognizable forms. Apply this to the Planck Epoch and the early universe's horizon. The limit of causal connection during inflation might have hosted similar firewalls, not annihilating information but encrypting it into quantum fluctuations. These fluctuations, once magnified by cosmic expansion, became the seeds for galaxies, subtly encoding the universe's birth story in their patterns. The stakes couldn't be higher. If information was truly lost during the Planck epoch, our understanding of quantum mechanics, and by extension, reality's bedrock, is flawed. But if it was preserved, even scrambled, the implications are staggering. The cosmic microwave background's temperature variations, the distribution of dark matter, even the arrow of time itself could be decipherable messages from that first instant. Some models suggest that the universe's initial quantum state might still be detectable in the polarization of ancient light, like a fingerprint on spacetime's oldest photograph. What's clear is that the Planck epoch didn't just set the stage for the universe, it tested the limits of physics itself. Whether through entanglement's delicate threads, firewalls' chaotic encryption, or some deeper mechanism still undiscovered, the cosmos found a way to inscribe its origin into existence. And as we peel back the layers of this paradox, we're not just exploring how the universe began. We're asking whether reality, at its core, is knowable at all. Scientists face a monumental challenge when trying to recreate the Planck epoch, a moment when energy densities eclipsed anything we can produce, and the laws of physics as we know them dissolve into uncertainty. Yet that hasn't stopped them from devising ingenious workarounds. One approach borrows from supercomputers and advanced mathematics, lattice quantum gravity. Imagine spacetime not as a smooth fabric but as a grid of tiny interconnected points, like a cosmic mesh where each intersection represents a quantum of space. By running simulations on these digital lattices, physicists can approximate how spacetime might have behaved when it was a seething quantum foam. The results are far from perfect. These models can't yet reach the energies of the true Planck scale, but they've offered tantalizing glimpses, such as how microscopic black holes might have flickered in and out of existence during those first moments. But digital simulations aren't the only tool in this cosmic detective kit. Some researchers are turning to analog experiments, using tabletop setups to mimic conditions akin to the early universe. Take Bose-Einstein condensates, ultra-cold gases where atoms move in eerie unison, behaving like a single quantum wave. By carefully manipulating these systems, scientists can simulate how quantum fluctuations might have seeded cosmic structures. Another bold experiment involves laser pulses fired into specialized crystals to recreate spacetime's hypothesized granularity. These lab-born universes are, of course, vastly simpler than the real thing, but they provide something pure theory can't: tangible data. When a ripple in a condensate mirrors predictions about primordial density variations, it's a hint that the models might be on the right track, yet the hurdles are staggering. The Planck epoch's energies are so extreme that even our most powerful particle colliders, like the Large Hadron Collider, fall short by a factor of 10 to the power of 20. And while lattice simulations can model quantum gravity's behavior at lower energies, they hit computational walls when approaching true Planck-scale conditions. It's like trying to predict a hurricane's path by studying the swirl of water in a teacup. The underlying physics might share similarities, but the scales are incomparable. Then there's the measurement problem. In the Planck epoch, spacetime itself was fluctuating, meaning any observer would have been part of the chaos, blurring the line between measurement and reality. Despite these limits, every failed simulation and every unexpected result teaches us something. When a supercomputer spits out a paradoxical singularity, it forces theorists back to the drawing board to refine their equations. When an analog experiment behaves in ways no one predicted, it might hint at undiscovered physics lurking beyond our models. Some of the most promising insights come from unexpected places, like quantum entanglement experiments that explore how information could have survived the Planck epoch's fury. Each effort, whether digital or analog, is a step toward answering the ultimate question: what laws could possibly govern a reality before space, time, and the very concept of laws as we know them existed? The quest to simulate the Planck epoch isn't just about recreating the past. It's a stress test for our most ambitious theories, from string theory to loop quantum gravity. If a model can't survive the journey back to the universe's first moment, it's a sign that something's missing. And while we may never build a perfect replica of that primordial inferno, the struggle to approximate it is already reshaping our understanding of reality. Every calculation, every laser pulse, every line of code brings us closer to deciphering the universe's original blueprint, 1/trillionth of a second at a time. While the Big Bang model dominates cosmology, it's not the only story science tells about our origins. Some theories propose the universe didn't emerge from nothingness but cycled through endless rebirths, a cosmic phoenix rising from its own ashes in an infinite loop. In bouncing cosmologies, the Planck Epoch wasn't a beginning but a turning point where a collapsing predecessor universe rebounded into expansion. Picture a rubber band stretched to its limit, then snapping back with enough energy to launch anew. Here, the extreme densities of the Planck scale act as nature's ultimate shock absorber, transforming collapse into creation through quantum gravity's strange mechanics. Unlike the Big Bang's fiery singularity, the bounce smooths the transition, preserving remnants of the previous cycle, like cosmic DNA passed between generations of universes. Other frameworks go further, suggesting spacetime itself might be emergent, not fundamental but bubbling up from something deeper, like steam condensing on a mirror. In these models, the Planck Epoch wasn't the first moment of time, but the moment time became time, crystallizing from a timeless quantum substrate. Think of it like watching a movie suddenly switch from static to picture. The static wasn't before the film, it was the raw material waiting to organize. This view recasts the Big Bang not as an explosion but as a phase transition, where the universe's underlying quantum bits snapped into alignment like iron filings near a magnet. The Planck Epoch's turbulence, then, was less a birth cry and more the shuffling of reality's deck before the cards were dealt. Yet another radical idea comes from conformal cyclic cosmology, where universes stretch and reset in infinite succession, connected by their far futures rather than their origins. As one cosmos expands into near-empty oblivion, its sparse particles lose all sense of scale, effectively resetting conditions to mirror the Planck Epoch's featureless energy. Like an endless symphony where the last note of each movement bends seamlessly into the next overture, the cycles inherit no information but share a mathematical symmetry. The Planck Epoch here isn't a beginning or an end, just a recurring chord in reality's score. What unites these alternatives is their reimagining of the Planck Epoch's role. In the standard model, it's an impenetrable wall where physics stops, but in bouncing or emergent scenarios, it's a bridge, a transformation layer where one state of reality morphs into another. Whether through quantum rebounds, thermodynamic resets, or geometric metamorphosis, these theories challenge us to see the Big Bang not as the ultimate origin, but as one event in a richer, more mysterious cosmic history. And that shift changes everything, because if the Planck Epoch wasn't time zero, our universe might carry whispers of something older, waiting to be decoded. The Planck Epoch doesn't just stretch the limits of physics, it forces us to confront questions that have haunted philosophers and theologians for millennia. If time, space, and matter as we know them emerged from a primordial state where conventional laws didn't apply, what does that mean for our understanding of creation itself? Some see the Big Bang as a scientific parallel to creatio ex nihilo, the idea that the universe sprang from nothing, but the Planck Epoch complicates this notion. Nothing in physics isn't empty, it's a seething quantum vacuum brimming with potential. The transition from that chaotic froth to an ordered cosmos blurs the line between scientific explanation and metaphysical wonder, leaving room for awe whether you approach it through equations or existential reflection. Causality faces its own reckoning here. We're accustomed to thinking in linear terms: cause precedes effect, the past shapes the future. But in the Planck Epoch, where time itself may have flickered unpredictably, this logic breaks down. Imagine a river flowing upstream or a symphony where the finale comes before the overture. If events in that first trillionth of a second weren't bound by the arrow of time as we experience it, then the very foundation of why and how becomes fluid. Theologians grappling with concepts of a timeless deity or theologians who argue for creatio continua, continuous creation, find surprising resonance with these physics models. The universe might not have been created in a single act but perpetually unfolds from a deeper, more enigmatic source. The nature of reality takes center stage in these debates. Is the universe fundamentally mathematical, as Plato suggested, with the Planck Epoch revealing the moment abstract geometry crystallized into physical law? Or is it more akin to a cosmic simulation where the Planck length represents the pixel size of an underlying code? Some Eastern philosophies, with their emphasis on cyclical time and illusionary separateness, find unexpected harmony with theories like the holographic principle or bouncing cosmologies. Meanwhile, existentialists might see the Planck Epoch's chaos as a metaphor for life's absurdity, a reminder that even the cosmos began in uncertainty. These intersections don't demand reconciliation. Science seeks mechanisms, philosophy and theology probe meaning, but the Planck Epoch's mysteries remind us that some questions transcend disciplines. Whether through the lens of quantum gravity or sacred texts, humanity stares into the same abyss, wondering not just how the universe began, but why there's anything at all. In that shared curiosity, perhaps, lies the most profound implication of all. The frontier of Planck Epoch research isn't waiting for some distant future. It's unfolding now in labs around the world, where scientists are engineering tools so precise they border on the miraculous. Quantum computers, with their qubits dancing in superposition, might become our first window into that primordial chaos. Unlike classical bits stuck in rigid zeros and ones, qubits exist in fluid quantum states, eerily reminiscent of the Planck era's blurred realities. Imagine programming such a machine to simulate how spacetime's fabric might have knotted and unknotted itself during those first moments. Current quantum processors like Google's Sycamore or IBM's Condor are already tackling simplified models of quantum gravity, where virtual spacetime pixels emerge from the interplay of entangled qubits. While today's noisy intermediate scale quantum devices can't yet recreate Planck-scale energies, each improvement in error correction brings us closer to mimicking conditions where gravity and quantum mechanics merge. But quantum computing isn't the only game in town. Next-generation particle colliders are pushing boundaries in unexpected ways. The proposed Future Circular Collider at CERN would dwarf the Large Hadron Collider, with a 54-mile ring designed to smash particles at energies approaching 100 tera-electronvolts, still far below Planck scale, but perhaps enough to produce exotic particles predicted by string theory or extra-dimensional models. These hypothetical entities, like supersymmetric partners or Kaluza-Klein modes, could carry echoes of the unified forces that dominated the Planck epoch. Even more radical is the plasma Wakefield accelerator concept, which uses laser-driven plasma waves to achieve acceleration gradients thousands of times stronger than conventional methods. If successful, this technology might one day deliver collision energies that flirt with the grand unified theory scale, offering indirect clues about how forces behaved before they split. Beyond brute force energy, precision cosmology offers another path. The upcoming laser interferometer space antenna will float in orbit, free from Earth's seismic noise, to detect gravitational waves with wavelengths far longer than ground-based observatories can catch. These ripples could carry signatures of cosmic strings, hypothetical defects in spacetime dating back to the Planck epoch, or reveal the gravitational afterglow of inflation itself. Meanwhile, the Simons Observatory in Chile's Atacama Desert is mapping the cosmic microwave background with such exquisite detail that it might spot the faint imprints of primordial black holes or quantum foam fluctuations frozen into the sky. Perhaps the most mind-bending experiments are those probing quantum gravity's effects without directly accessing Planck energies. Tabletop setups using supercooled atoms or superconducting circuits are testing whether spacetime really is smooth or if it fractures into discrete grains at microscopic scales. One particularly elegant experiment at the University of Chicago suspends a tiny mirrored membrane in a quantum superposition, watching for telltale jitters that could betray spacetime's underlying graininess. Others hunt for deviations in the speed of light across different wavelengths, a potential smoking gun for spacetime's quantum structure, the common thread. Every approach is a workaround, a clever end run past technological limits. We may never recreate the Planck Epoch's raw energy, but by combining quantum simulations, ultra-precise measurements, and cosmic archaeology, we're assembling a mosaic of indirect evidence. Each fragment, whether from a qubit's dance, a collider's debris, or a telescope's whisper, brings us closer to decoding reality's first and most elusive chapter. Einstein's vision of gravity as the elegant curvature of spacetime and quantum mechanics' chaotic dance of particles seem irreconcilable until you rewind to the Planck Epoch. Here, in the universe's first trillionth of a second, these titanic theories collide with unavoidable force. General relativity paints gravity as a smooth geometric tapestry, while quantum mechanics insists reality is pixelated, flickering with uncertainty. Under ordinary conditions, they ignore each other like two languages describing separate worlds. But in the Planck Epoch's inferno, where spacetime was compressed to a billionth of a trillionth of a proton's width, both theories break down, screaming for a deeper truth. This isn't just a theoretical clash, it's a fight for the soul of physics, and the stakes couldn't be higher. Enter loop quantum gravity, one audacious attempt to broker peace. Imagine spacetime not as a seamless fabric but as a woven tapestry of tiny, indivisible loops. Think of a mesh where each thread is a quantum of area, vibrating with its own rhythm. In this framework, the Planck Epoch's chaos wasn't infinite density but a frenetic reorganization of these loops, a cosmic knot tightening until it rebounded into expansion. No singularities, no infinities, just a quantum network reaching its limit and bouncing back. It's a radical rewrite of Einstein's equations, where gravity emerges from the spin and weave of these fundamental threads. The beauty, it eliminates the Big Bang's division by zero flaw by giving spacetime an atomic structure, a smallest possible stitch in reality's quilt. Yet loop quantum gravity isn't the only contender. String theory takes a wildly different approach, proposing that particles aren't dots but vibrating strings, each harmonic resonance birthing a different particle or force. In the Planck Epoch's heat, these strings wouldn't just wiggle, they'd be spacetime itself, tangled in higher dimensions we can't perceive. Here, gravity isn't a standalone force but another note in the string's symphony, unified with the others through sheer vibrational harmony. The theory's elegance lies in its ability to smooth over the Planck Epoch's paradoxes. Strings can't collapse to a point, so no singularities arise, just a dense, vibrating web where the universe's laws are still negotiating their terms. But neither theory has a monopoly on truth. Some physicists argue we're missing a third path, something like causal dynamical triangulation, where spacetime assembles itself from geometric building blocks, or emergent gravity, which suggests gravity isn't fundamental but a side effect of quantum entanglement. Others speculate that the Planck Epoch's resolution might require entirely new mathematics, frameworks where concepts like before and after lose meaning and causality becomes fluid. The challenge is stark. Any theory must explain not just how gravity and quantum mechanics reconcile, but why their union birthed a universe with stars, planets, and us. What makes this showdown so electrifying is how it reframes the Planck Epoch. It's not just a moment in time, it's a filter for ideas, a cosmic crucible where only the most robust theories survive. Every calculation, every simulation, every flicker of data from particle colliders or quantum computers is a step toward glimpsing that primordial conflict. And somewhere in the haze of equations and experiments lies the answer to physics' ultimate question. What law could possibly govern a reality before space, time, or even law itself existed? Cracking the Planck Epoch's mysteries wouldn't just fill a gap in our cosmic origin story, it could shatter the foundations of modern physics as we know them. Picture the Standard Model, that meticulously crafted catalogue of particles and forces, suddenly expanding to accommodate an entirely new layer of reality. The discovery of quantum gravity's rules might reveal particles beyond our wildest theories, not just heavier versions of quarks or neutrinos, but entities that blur the line between matter and spacetime itself. Some theorists speculate these could include gravitons carrying quantum whispers of gravity, or even chronons that mediate time's flow at fundamental scales. Such finds wouldn't just complete the periodic table of physics, they'd rip up the tablecloth and reveal an entirely new kind of furniture beneath. Energy production could undergo a similar revolution. If we decipher how the Planck Epoch's unified force fractured into gravity, electromagnetism, and nuclear forces, we might learn to reverse the process harnessing energy not from chemical bonds or fission, but from the primal interactions that preceded them. Imagine reactors tapping into the same quantum symmetries that powered the Big Bang itself, where infinitesimal amounts of vacuum energy could yield outputs dwarfing nuclear fusion. The catch: these technologies would require manipulating spacetime at scales 1 trillion times smaller than atoms, a challenge akin to threading a needle with a thread that doesn't yet exist. The most speculative and tantalizing possibilities involve spacetime engineering. If the Planck Epoch shows spacetime is emergent rather than fundamental, could we learn to reweave its fabric? Wormholes, often dismissed as science fiction, might become mathematically plausible if we uncover how spacetime's threads knotted themselves during cosmic inflation. Even modest breakthroughs could lead to gravity shielding or inertial dampening, concepts that sound absurd today but might seem obvious once we grasp quantum gravity's grammar. These wouldn't just revolutionize space travel, they'd redefine mobility itself, turning metrics like distance and acceleration into adjustable parameters rather than fixed laws. Yet perhaps the most profound shift would be philosophical. Solving the Planck Epoch could force us to abandon the very notion of laws of physics in favor of something more fluid, a cosmic operating system where constants like the speed of light or Planck's quantum aren't fixed but frozen accidents from the universe's first shudder. This wouldn't just change textbooks, it would alter humanity's place in the cosmos, revealing our reality as one possible configuration in an infinite meta-landscape of physics. The Planck Epoch's resolution might not just explain how our universe began, but expose the mechanisms allowing anything to exist at all. For now, these ideas remain dreams sketched in equations. But history shows that today's wild speculations often become tomorrow's foundational truth. If we dare to follow the math wherever it leads, back to that first impossible moment when all the rules were still being written. The Planck Epoch may have lasted less than 1 trillionth of a second, but its legacy stretches across every atom, every galaxy, and every law of physics we take for granted. This wasn't just the universe's first chapter, it was the moment reality drafted its own rulebook, when gravity, quantum forces, and spacetime itself were forged in conditions so extreme they defy imagination. Think of it as the cosmic equivalent of a master key, a fleeting instant that somehow locked in the constants and symmetries governing everything from the spin of electrons to the expansion of the cosmos. And here's the astonishing part, we're still deciphering its fingerprints. Consider how much we've pieced together already. Quantum fluctuations smaller than atoms became galaxies. A unified force fractured into the interactions that light up stars and hold molecules together. Spacetime itself crystallized from a seething quantum foam. Yet for every answer, the Planck Epoch reveals deeper questions. Why these particular laws? Was the balance between matter and energy inevitable, or a cosmic roll of the dice? Could different universes with entirely different physics have emerged from that same primordial fire? These aren't just academic puzzles. They're clues to whether our universe is finely tuned for life by accident or necessity. What makes this era so electrifying isn't just its past significance, it's its living mystery. Right now, buried in the math of quantum gravity theories or hidden in the data from particle colliders, might lie the next breakthrough. When researchers probe spacetime's granularity with tabletop experiments or simulate black holes on quantum computers, they're not just testing abstract ideas. They're reverse engineering creation. Even failures illuminate the path forward, narrowing the infinite possibilities of what those first moments could have been. So stay curious, follow those gravitational wave detections, those debates over string theory's extra dimensions, those tiny anomalies in cosmic microwave background maps. Because the Planck Epoch isn't some distant, untouchable relic. Its echoes surround us, woven into the fabric of everyday reality. And with each new discovery, we're not just learning how the universe began, we're uncovering what it fundamentally is. The next revelation could come from a telescope, a chalkboard, or an experiment no one's even dreamed up yet. The only certainty, however strange the answers turn out to be, they'll be stranger than we imagined. The cosmos has always been full of surprises, starting with that very first cosmic blink.